So continuing on with quantifiers now, one of the things that we definitely need to be able to do is to negate quantifiers. So we need to do this both to prove that a statement is false, and the way we do that is actually to prove that its negation is true. So we need to be able to form its negation. Then we also need to be able to negate quantified statements because they may appear inside something for which we're going to form the contrapositive, where we definitely need to be able to negate the hypothesis and conclusion and to form that contrapositive. Okay, so let's learn about negating quantifiers. So consider this statement. Consider the statement for all n squared plus 1 is prime. Now in order for this to be true, we've got to show it's true for every single value of n. So let's start exploring that. So when we do start exploring that, and see when n is 1, we get 1 squared plus 1 is 2 is prime, that's good. N is 2 gives us 4, 2 squared is 4 plus 1 is 5, that's prime. N is 3, we get 3 squared is 9 plus 1 is 10, which is definitely not prime. So because this doesn't work for every single value of n, indeed here's one value of n for which it doesn't work, we've shown that this statement is false. Now what we've actually just done is we've proved that its negation is a true statement. So if you think about what we just did here, we found a value of n, at least 1, for which n squared plus 1 is not prime. And so this statement down here with this universal quantifier became an existential quantifier, open sentence n squared plus 1 is prime, its negation appears here, n squared plus 1 is not prime. This statement down here is the negation of our original statement. So the negation of for all becomes there exists. And we'll do this more carefully in a second, we'll write this up carefully. But let's do another example. Consider this statement. There exists n so that n squared is less than n. Okay, so we're pulling n from the set of natural numbers, so again we should explore this a little bit. So when n is 1, n squared is 1, which is equal to 1. So that doesn't work. N is 2, we get 4, which is definitely bigger than 2, so that doesn't work. N is 3, 3 squared is 9, bigger than 3, that doesn't work. So it certainly looks like this is false. But remember, in order for this to be true, we just have to find one value that makes it true. So in order to show it's false, it's not enough to give some examples because we don't know that if we just looked a little bit further, we wouldn't find one that made it work. Okay, so we need to show that it's actually not going to work, namely that n squared is bigger than or equal to n for every single value of n in the natural numbers. That is, for all natural numbers n squared is bigger than or equal to n. Okay? So in order for the original statement to be true, there just has to be one value that makes it work. So in order for this to be false, every single value of n fails. Okay? So again, the negation of an existential quantifier becomes a universal quantifier and vice versa. So let's write this down as a theorem. So let P of x be some open sentence over a given domain A. That is, we're pulling the values of x out of that set A. Well then, the negation of for all x in A, P of x, is equivalent to there exists x in A so that not P of x. Okay, so we can sort of think about pushing this negation symbol through the quantified statement. It pushes past for all and becomes there exists. And then the negation symbol winds up attached to the open sentence. So negation of for all becomes there exists not. Similarly, when we negate there exists, so negation of there exists x in A, so it's the P of x, becomes for all x in A, not P of x. Okay, so negate for all becomes there exists, negates there exists becomes for all. Okay, so they sort of twin to each other through negation. But notice here, the domain doesn't change. This is still for all x in A, for all x in A. For all x, there exists x in A, x in A. Okay, the negated statement still has the same domain. Okay, so we have to be very careful of this. When we negate a quantified statement, the domain stays the same. Okay, so I've summarized this here. Be careful of this. So it's definitely not the case that when we negate for all x in A becomes there exists, for all x not in A. Okay, this doesn't make sense. Okay, the domain doesn't change. So don't do this. This is bad. Okay, like writing on top of yourself, that's bad. Okay, I'm going to lean to one side here and point to remind you, please don't do this. When we negate a quantifier, the domain stays the same. Okay. So let's look at a good example or two now. Okay, so here's an example. There exists some natural number n so that 4 divides n squared plus 1. Now, to prove this true, we just need to find a value of n that makes it work. We just need to show the person reading our proof, here's the value of n, you can check it. It works. But to prove it's false, we need to show that its negation is a true statement. Okay, so let's explore it a little bit by doing a little scratch work. So we just plug in some values of n and try it out. When n is 1, n squared plus 1 is 2. So that doesn't work. 2 is not divisible by 4. n is 2, we get 4 plus 1 is 5. That doesn't work. n is 3, 9 plus 1, 10. That doesn't work. n is 4, 16 plus 1, 17. That doesn't work. Okay, so it definitely looks like it's going to be false. Indeed, we see if n is even, well, we worked that out before. When n is even, n squared is even. So n squared plus 1 is going to be odd. So it certainly doesn't look like it's going to be true when n is even. Okay. So it certainly smells false. So we should look at the negation here. Now what I'm trying to do here is show you the process by which we might explore whether a quantified statement is true or not. We can plug in some values to test it out, to get the feel for what's happening. And then if it looks like it's going to be false, we should look at its negation. And so when we negate this statement, there exists becomes for all, and then the open sentence becomes negated. So 4 divides n squared plus 1 becomes 4 doesn't divide n squared plus 1. Now, I've got a bit of incorrect notation here, that should just be a comma. Okay? So for all n in n, 4 does not divide this. Okay? And as we saw here, there's some odd even effect here, so it sort of smells like maybe we can do something with the parity of n, which also starts to look like a proof by cases. So now we're trying to prove the statement that for all n in n, 4 doesn't divide n squared plus 1. And we're going to try playing with the fact that if n is even or n is odd, maybe we can see a bit more. So again, some scratch work. If n is even, n is 2k, so n squared plus 1 is 4k squared plus 1. So it's 4 times an integer plus 1, not divisible by 4. If n is odd, n is 2l plus 1. So n squared plus 1 is 4l squared plus 4l plus 2. Okay, just doing the algebra. And so again, because it's 4 times an integer plus 2, it's not divisible by 2. Okay, so let's write this up as a proof. So we're going to tell the reader we show the statement is false by proving its negation to be true. So we're telling the reader what's going on here. Now, since n is even, since n is in the natural numbers, it's either even or odd. Now, assume n is even, so n is 2k, and thus n squared plus 1 is 4k squared plus 1. If we assume, on the other hand, that n is odd, then we can write n as 2l plus 1, so n squared plus 1 is 4l squared plus 4l plus 2. In both cases, by Euclidean division, the result is not divisible by 4, because this is 4 times an integer plus 1, 4 times some other integer plus 2. And so we're done. Now this proof is perhaps a little bit brief, and we should probably actually put in some more information here, because I've just said n is 2k, or n is 2l plus 1, and I haven't told the reader where those have come from. So somewhere around here and around here, I should really add k is an integer, or l is an integer. Okay, so I should really add that bit of information into the proof around here and here. And again, we could put in a bit more information to highlight the fact that this is 4 times something plus 1 and 4 times something plus 2. So we could put in a little bit more information for the reader around here if we were trying to be a little bit kinder to them. That might be a good idea. So this proof is maybe a little bit terse when we're starting out, and we should probably amend it in the ways that I just suggested. Okay, I'm going to stop there. Thank you.